So yesterday we discussed an example of a non-trivial fixed point. That non-trivial fixed point was what's called the Wilson-Fisher fixed point. And it was an example of an infrared fixed point. So basically what was happening in coupling constant space, there is always a Gaussian fixed point which corresponds to the free theory, free massless theory, and we found that we started with a theory which had relevant directions. All the directions are relevant. So these were the relevant directions. So actually found that the eigen directions are not really this, but they're somewhat slanted, but these flows ended up in another fixed point which is the Wilson-Fisher fixed point. So far as this fixed point is concerned, there is only one relevant operator, and anywhere you start in the coupling constant space, you end up flowing along that line with a single relevant operator, and therefore it just describes a theory in the infrared, a theory which has correlations which are short range with a finite correlation length. Except when you fine tune all your coupling so that it lies exactly on this line, because when it lies exactly on this line, it doesn't flow all the way up, it goes and settles down out here, and out here the theory has a fixed point, the beta functions are 0, and it has long range correlations. So you get the conclusion that if you tune parameters such that you are lying on this line, then the long range behavior of the theory corresponds to infinite correlation length. That's what we call critical behavior. When you start off anywhere else, you are going to land up with a massive a theory which has a finite correlation length. Okay, everybody understands this point? Good. So today we will discuss a model where a class of models where this was in 3 dimensions, but we wrote 3 as actually 4 minus epsilon with epsilon equal to 1, but we nevertheless did an expansion in epsilon and an expansion in the coupling constant u, and you are quite justified if you feel very uncomfortable about it, because it looks a bit strange. We will do something a little bit better today. What we will do is provide an example of what is called an ultraviolet fixed point. We will again eventually get to a model in 3 dimensions, and for us it will be just necessary to talk about, it's good enough to talk about just a single coupling constant, because I sort of know what the relevant couplings in the theory are. You start out on that plane, just as here I didn't really talk about phi 6th and phi 8th or something like that. I will just talk about here something which just looks like that. But at the Gaussian fixed point, we will find that the theory, this coupling is irrelevant, which seems to suggest that wherever you start, it will end up at that fixed point, and since it is a Gaussian theory, it will just have some trivial long range correlation. Okay. There is no, we will find that this theory, if this was the picture, it would have no interactions. This is in fact the correct picture for d equal to 4. This is an incorrect picture for d less than or equal to 3. In fact, we will find that when d equal to 3, there is a non-trivial fixed point from which these flows emerge, which actually separate 2 phases of the system. In one phase, if you look at the long distance behavior, you will find things corresponding to the Gaussian point, and in the other phase it will flow to some massive theory with a finite correlation length. Okay. For d equal to, greater than or equal to 4. This does not happen, this fixed point actually goes all the way to infinity, and for d equal to 2, it is an interesting case, this thing moves all the way to 0 and the coupling actually happens to be relevant. Okay. This is an example of what is called an asymptotically free theory. And it played a very important role. This thing plays a very important role in a wide variety of situations, all the way from the proof of the from formulations of string theory to pure mathematics in the proof of the Poincare conjecture. This is the whole thing related called Ricci flows. Okay, I'll probably not discuss that, but let me just do the simplest version of this sigma model. The model has action, phi I are n real scalar fields. There is a sum upon I, of course. Anytime there is a two i's, I mean there is a sum upon I. With the constraint, actually I'll do it in a slightly different way. I'll write a I integral d dx to g square if this condition was not there, this would be trivial, just a free field theory, nothing about it, right? We know how to do this functional integrals and everything. See, it's this condition that complicates the matter. So let me tell you a little bit about the motivation for writing a model like this. These models appear in particle physics, first written down by Gell-Mann and Levy in the 50s to describe the low energy behavior of pions, low energy effective action for pions. We will see why that is true later on. I don't expect you to appreciate that. But when we think about it, this is in fact the Heisenberg model for magnets, written like that, okay. So the Heisenberg model for magnets consists of, if you write it on a lattice, it consists of an energy functional which is like this. I write A, B, these are the sites, A nearest neighbor, with spin vectors at each site, except the square of this thing. So phi I is a 3 component vector. I runs from 1 to 3. A and B are sites on the lattice. So phi I are the components of a spin, and in the classical limit, phi I square sum upon I, the magnitude of the fin is fixed. I don't know, S times S plus 1, whatever you like, some fixed magnitude. The spins are just rotating like this. This is one of the oldest and most successful models of a magnet. You can see that this model is exactly the same as that, except that you have to rescale the fields phi by whatever power, and then there will be a 1 upon something which comes out here. Okay. Classically, what do you expect in this theory? Classically, what you expect in this theory is the following. Since the magnitude of the spin is fixed to be like that, what you would expect that classically the spins would just align themselves, and there is an expectation value of the square of the spin. That is what this constraint tells you. We will see that quantum mechanically we will see otherwise. In quantum, I mean when you do the quantum field theory, you will see that something very sort of non-trivial happens and we will see how that happens. I will take the index from 1 to n, in which case it is called the ON nonlinear sigma model. The reason it is called ON is because it has a symmetry where phi goes to O times phi, where O is an orthogonal n by n matrix, because that keeps the constraint invariant, it certainly keeps the action invariant. Okay? It's just think of vectors not living in 3 dimensions, but vector living in n dimensions. So if the vectors were living in 3 dimensions, the symmetry is the rotation group, which is O3. If the vectors are living in n dimensions, the theory is a symmetry, which is the orthogonal group, which is ON. Okay. We are going to solve this. It came because that's actually historical. So let me come back to that question later on. Sigma is the fluctuation of the magnitude of things. This came actually a limit of what is called the linear sigma model, where the magnitude of phi was not constrained to be 1, it was left field, but there was a potential, and the potential told you what the magnitude of phi is, and that magnitude is called sigma. I mean, it is historical. Sigma is the name of a particle in strong interactions. This model was discovered for strong interactions by Gell-Mann and Levy. Okay, we are going to solve this problem. We will find how we can explicitly solve this problem in the large n limit, and we will see why this limit is sort of interesting. This limit consists of n going to infinity and the combination g square n being held fixed. Okay. So that requires, it is a limit when g is very small, n is very large, such their product g square n is some fixed number lambda. We will calculate all properties of this theory as a function of lambda in this limit. Okay. I will call this G as a coupling of the theories. Now, coupling usually means some non-linearity. So why do I call G as a coupling? So let me point out why G is a coupling. The way this model is written, it is clear that all the fields phi are not independent of each other. We always have to satisfy this condition. So why not do the following? Let us solve let us solve for one of the components, for example phi 1. Okay. So let us do something else first. Let us write phi I as square root of g psi I. I have done nothing but redefine new fields. Then the action is just half integral d dx d psi I square, and the constraint now reads psi I is equal to 1 upon g square. Now this is sort of good because the coefficient of the conventional coefficient of the kinetic term is just a standard half. Okay. Now what I do, I solve for psi 1 as 1 upon g square minus psi I. This is a solution of this thing, and I substitute. So S is dtx d psi 1 square plus ddx d psi I square. This thing remains the way it is. Here I have to substitute for psi 1 using this equation, then of course I get something extremely non-trivial. So if you work it out, what you find is that this becomes, this is a half, this is a half, half, okay. So and plus and let's bring the g up there. So this is 1 minus g square psi I, and what appears here is half g square. And then I substitute, I'll mix upper and lower indices, substitute this thing in here, calculate derivative of psi 1. Here, I solve this equation. So this equation is psi 1 square plus psi I square equal to 1 upon g square. So psi 1 square is 1 upon. So this sorry, I should tell you. So here let me call it, let me write explicitly 2 to n so in this expression all the psi i's I runs from 2 to n, and as you can see the effect of having this constraint is telling you that I have a highly non-trivial interacting theory, highly nonlinear pieces, right, and which are all proportional to g square. So G is genuinely the coupling of the theory. Huh? Root G, yeah. Oh, you're right. Yes, to be G times. Good. Sorry. Yeah. So the from here the dimension of psi is of course d minus 2 by 2 right. Okay, so the dimension of it is d minus 2 by 2 because if you just put it in this term as d minus 2 and then plus 2 from the derivative, and that cancels the d out here. So that's the canonical dimension of a scalar field in d dimensions, and therefore the equation psi square equal to 1 upon g square tells you dimension of 1 upon g square is d minus 2. So the dimension of g square is 2 minus d. Okay. So this tells you that for d equal to 2, this is a dimensionless quantity. Okay, a dimensionless quantity naively is what? A marginal operator. It doesn't, there is no power of lambda or anything. So if you scale lambda, nothing really happens to it. So it is a marginal operator naively. For dimension 3, 4, etc., it's an irrelevant operator. So naively you would think that for dimensions 3, 4, 5, whatever, that if I look at the extreme low energy limit of the theory, or really speaking the continuum theory where I take the cutoff to infinity, this theory should be trivial, because all the couplings should go to 0, right. That is what an irrelevant operator means. It is there is just a Gaussian fixed point at g equal to 0. So that means those psi i's, the independent psi i's, do not interact with each other. So what we will find, that there is something highly non-trivial which happens when d equal to 3, that this is not really the story. For d equal to 2, you might think g is just dimensionless, it is a marginal operator. Naively, that is indeed true. We will find that once you actually do the quantum field theory of this, it is not a marginal operator anymore, it will turn out to be a relevant operator. A relevant operator means that in the infrared, in long distance, the interactions become very important. So it is a highly interacting theory. It develops a mass cap, because a relevant operator comes with a mass scale. It is pretty much like a mass. We will show that it will actually acquire a mass. These fields will actually acquire a mass, they will not massless. And for d equal to 3, we will see that it actually develops a phase transition, a transition between an ordered phase and a disordered phase. Fair enough, because magnets in 3 dimensions are well known to have phase transitions between an ordered and a disordered phase. Magnets in 2 dimensions do not have phase transitions. Okay. How do we solve the problem? Here is a trick to solve this problem. You write the theory not in this form, times a delta function like this, and that I will write as, I will argue why this is the same as that. Okay. Why is that? I mean, it's I said not really a Lagrange multiplier, because I didn't put in an I. If I put in an I out here, there is still an integral here over d dx. Put in an I, it will be genuinely a Lagrange multiplier, but it is not really a Lagrange multiplier, because there is no I here. But it does not matter. I can continue the integral over sigma over the imaginary axis, and then it really becomes a Lagrange multiplier. Okay. The basic idea is that if we do the integration over sigma, I mean sigma being interpreted as an analytic continuation of this integral, you will get the condition phi square equal to 1 upon g square, and then it will be equivalent to the original model. But if we keep the integration over sigma, we will see that we will be able to do something interesting. Okay. Now, in our rules of function and integrals, we had a basic formula in order to do this integral, we did a Fourier transform. And then we found that this object is a product over vol k of k square plus m square raised to the power half. Okay. But the way it happened was to use the formula for the Gaussian integral. Sum upon I and j, and then we writing it in terms of k, we are already writing this in terms of the eigenvectors of Bij and the eigenvalues which are Bi square, and that answer was square root of pi upon Bi product over all I. This form of the answer is exactly like that form of the answer, right? This is clear? Because here you can see that once you put this thing in, this just becomes half dk k square plus n square phi k phi minus. It's sort of diagonal in k space. That's the whole purpose of doing a Fourier transform. But this, in any other basis, this had an answer which has determinant of b raised to the power minus half. The determinant doesn't depend on what basis you consider. If you use the eigenbasis of the matrix B, it just reduces to that formula. Forget about root pi is 1, forget about that. Then so I should be able to write down something, you know, formally for just this integral, okay. So just by sheer analogy this answer is in fact determinant of an operator raised to the power minus half. And what do you mean by determinant of an operator? Determinant of a matrix is what? Is a product of eigenvalues, right? So determinant of an operator, a product of eigenvalues of the operator, no big deal, okay. So the way you want to solve for the determinant is to take that operator, solve the eigenvalue equation, find the eigenvalues, take the product. But this is just a cute way of writing that is determinant of this operator. Okay. If you recall, I want to solve this in the limit n tending to infinity, g tending to 0, g square n fixed. So let me do something. Let me write this as n upon g square n, no big deal, and write this thing separated out what should I do? Just 1 second. I'll put a minus sign. The analytic continuation I did a bit wrong actually. Put a minus sign there. So I'll put plus n sigma upon lambda. So lambda is defined as g square n. I bring out just the thing which doesn't depend on the phi, and then I have an integral over d phi I runs from 1 to n, exponential of d dx half d phi. The vector notation is quite clear, right? I mean this way, and plus sigma. Can you put a, did I put a half here or? Just give me a minute. I'll put a half here. Why not? Sigma is an integration variable. So I put a half everywhere, and this becomes also very nice. This looks pretty much like that, except that sigma is a function of x. Okay, sigma is not, sigma was a function of x here, right? So I should write this explicitly as x. And but that doesn't matter. I still can do the integration over phi because now it's a Gaussian integral. So let me write down what that integral is and see what happens. Exponential of n sigma by 2 lambda and determinant again. The meaning of this determinant is as follows. So meaning of this determinant is you solve the eigenvalue equation for it's not a bad equation to solve, 2-dimensional Schrodinger type equation you are using in some potential. So if you know what sigma of for a given sigma x, you can solve for the eigenvalues. Of course, the eigenvalues E will depend on sigma of x, and the determinant of that is just the product of the possible eigenvalues. That is the definition. Yes, this will power upon n upon 2 because there are n such integrals. But all the integrals are identical, all the n integrals are identical, it is n upon 2. Now there is a nice formula for the determinant which will now turn out to be handy. A determinant of a matrix is an exponential of a trace log of that matrix. I leave it as an exercise for you to prove this formula. So I will write this as and I will put the n in fact outside. Let me put n outside. So this is an integral over x. It's an integral over x. N is completely outside. Both the terms have n in it. Okay? If I try to do an integral like this, like integral dx some lambda times function of x, then if lambda is very very large, I mean roughly speaking you should take this thing outside, say minus lambda times f of x, and if lambda is a positive quantity and very very large, then almost all x's will give a vanishing contribution to this integral, and the only x's which will give any contribution at all are the saddle points of f. So what you need to find is to find the saddle points of this entire object. This is the reason why quantum mechanics reduces to classical mechanics. Classical mechanics is the saddle point of quantum mechanics in the limit h bar going to 0, except that h bar going to 0 as a statement does not make any sense. You have to find the dimensionless quantity which goes to 0. So it is typically the action divided by h bar which goes to 0. In this case there is a dimensionless quantity n, so the analog of h bar is 1 upon n. So this tells you 1 upon n sort of behaves like an h bar. Remember this statement, we will make great use of this statement later on. The large n limit is a classical limit in some sense. It is not classical in the sense of fluctuations of the original fields phi r, they are madly fluctuating. I have integrated them completely. It is classical in some other way, and we will try to make this thing a little more accurate. Trace so equal to 0. So that tells you this derivative gives 1 upon 2 lambda, and that gives you a trace derivative of log with respect to sigma just brings the inverse operator down. Now this is a bit too abstract at the moment. Very soon we will make it like as concrete as you like. So this is the equation I have to solve. typically not very easy to solve, because the sigma of x is a function of x. These are highly complicated, object to calculate. But however, if you think physically, this is a Euclidean functional integral, and if there is any justice in the world, the minimum of that functional integral should have a constant value of sigma. And the reason for that is that if you write this thing, you can expand this thing around. So you can sort of write this as and expand in binomial series. So essentially what happens is that if you do this calculation, what you find that even though there was no term like del sigma whole square or anything like that, it will acquire terms which have del sigma whole square when you actually calculate this integral, and those will always give some positive action to the answer, and generally speaking you would have a saddle point where sigma of x is a constant. Okay. It basically tells you that if there is a system with some symmetry, there is a symmetry in the system which is translations in space, and typically the lowest energy solution always respects the symmetry. Now there are cases it doesn't, those are interesting cases, but in this case it so happens that that's quite a triviality. So we will try to look for a translationally invariant saddle point. That means if I call the saddle point to be this configuration, so sigma of x is sigma 0, which is a constant. Okay. So this equation now becomes this, and this is very easy to write explicitly. The reason why this is very easy to write explicitly is because what is a trace? Trace is over, you can trace is over a complete set of vectors in the vector space, and you can, and basically in a quantum mechanical notation you can write is integral over d dx x, but by the completeness of thing you can also write where these are eigenstates of x, right. So I can also write in terms of eigenstates of the momentum operator. So this equation becomes extremely simple but tells you a lot of deep things about the problem. So this is called a gap equation. There was a half of which I missed. So this is 1 upon lambda. I am just putting all the factors of 2 pi to the power d just to impress you. So it's just 1 upon k square per sigma. You got to do this integral. If you are able to do the integral on the right hand side, you will get sigma as a function of lambda, and that's what we want. So let's do this integral. So this integral is the volume of the d minus 1 dimensional unit sphere times 2 to the d. I just went to polar coordinates in k space, and in principle this should go from 0 to infinity, but wait a moment, it cannot go from 0 to infinity. Something will be troublesome, at least for large values of d, because for example if any d is equal to 3, one of the cases we will be interested in. So this is For large values of d, this is like integral dk, it's linearly divergent. Okay? This just tells you, you should never do quantum field theory without putting a cutoff. First put the cutoff and then get rid of it. So let's put a cutoff. And what is this integral? It turns out you can do this integral. I mean, it's not hard to do this integral, but I won't do it. I'll do a special cases of this, but for that,
is it the form of this equation which you are trying to solve, that sigma equal to this, whatever you are talking about? So that's why you are looking for the translation.
for d equal to 2, 2 minus 1 is 2 pi, right? So this is a thing. So d equal to 2 is omega 1 means a one dimensional sphere, another name for it is a circle. The size of a circle is 2 pi. So that's 2 pi. This one is 2 pi whole square, and I'll put a half here, and like d of k square divided by k square plus sigma naught from 0 to lambda. That's 1 upon 4 pi, and this is what log we are looking for solutions where sigma 0 is much smaller than the cutoff. It will become very clear why we are doing that in if you just give me a minute, in which case I can replace sigma 0 plus lambda square, this is lambda square, by just log of lambda square. So lambda is very large, so that's the thing, same thing as 4 pi lambda square log of lambda square by sigma 0. So bloody da, so that's equal to 1 upon lambda. So sigma 0 by lambda square is exponential of minus 4 pi upon lambda. Sigma 0 Now, let us take a little step backwards from what we did. We just did the saddle point, namely at n equal to infinity, I found the value of sigma 0, right? And like a limit is not a good limit if you are not able to go away from it, right? So what we should do is to calculate the next order in an expansion in 1 upon n. Okay. So what do you do to that? So what you are going to do is, you had a integral and for n equal to infinity, because of integrating out the phi, I got an additional factor of n, and for n equal to infinity I found that sigma is sort of peaked at a value of sigma 0, right. So surely this cannot be the exact, if I were to able to calculate the average of sigma, it will be sigma 0 plus by terms which are typically of order 1 upon n, because clearly if I do that thing exactly, it will not be sigma 0. It will only be sigma 0 in the n equal to infinity limit, right. So what you really need to do with this is to expand the fields sigma 0 as sigma 0 plus delta sigma, okay, and you have to put a suitable factor of n in order to get the, I think the factor of n is this, and you have to write phi. The phi didn't have an expectation value here at the moment, so it's just going to be phi, okay. But now see what happens. This term becomes d phi whole square plus sigma 0 phi whole square plus delta sigma phi square. You have two fields in the problem, phi and sigma 0, sigma phi and sigma. This term gives rise to a mass for the field phi. There was nothing like that to begin with, okay. To begin with, the phi didn't have any mass. In fact, when we wrote the nonlinear sigma model and wrote it in terms of those independent fields didn't have a mass, okay. If you just remember, the independent fields had an action which was like this, and then there was like psi d psi, psi d psi, and then there was a g square 1 minus psi square. And if you look at small psi and expand this, the inverse of that, you never get a term which is psi square, which is the mass term. It comes with psi del psi, psi del psi, you know, psi del psi, psi del psi, psi square, and all kinds of other junk, but never a mass. Okay, so what happened? The theory developed a mass, and the theory developed a mass in a way which is non-perturbative in the coupling, as we will show in the moment. But then you say, wait a moment, you developed a mass sigma 0, and I find a formula for sigma 0, which is mass square, sigma 0 is mass square, is lambda square or something, and you will just immediately tell me, this guy has been bullshitting from day one, saying that all we are interested in are masses which are much smaller than the cutoff. So what's going on? You get a mass which is of the order of the cutoff. I thought we are not interested in that. Lambda is held fixed in the large n limit. Lambda is not small. I have never assumed lambda is small. G was small. G square n was finite. You had a flow which sort of looks like this. Okay, and then he said that, okay, let me just write down a theory which is parameterized by a single parameter. So namely, the relevant, irrelevant, or the thousands of operators, they have some fixed ratios, for example, some single relationships between them, and just one parameter remains like that. Our G is a parameter like that. Okay, except that I've sort of chosen it cleverly that we are sort of basically lying in a line, in a single line which is called the renormalized subspace of the theory. But nevertheless, then we said that this parameter is a line which describes for me a microscopic theory. That parameter was a dimensionless parameter. It described a microscopic theory. Okay, and then I want to say that I want to, however, describe physical objects which have masses which are something I give it to you. I mean, after all, the order was to describe, say, a theory of the pion or Higgs boson or whatever. It has some mass, whatever you have. And then he said, aha, then the way to do it, of course, is to associate each point in this line with a cutoff. So each microscopic theory, which I wrote as a lattice theory, there was no notion of a lattice spacing to begin with. It was just numbers put in a computer program, and then I say I'll ascribe this to have a lattice spacing, say 1 angstrom. Okay, and then each of these theories, which has different values of this parameter, I will say that as I change the parameter, I'm also changing the cutoff of the theory in such a way that the physical correlation length which is measured here is kept fixed. So basically, there was a parameter in the theory like m physical that You had M naught, which is dimensionless, there was an M physical times the lattice spacing, or M physical times divided by the cutoff, and I said that M physical is a parameter of the theory which is some number. That number has different values on different points, and I will say that for each value of that number I will associate a lambda which is M physical by M naught. Then I am guaranteed that whatever a theory I get in the infrared is going to have a physical mass given by M physical. So I should do the same thing here. Lambda was in 2 dimensions was a dimensionless parameter which parameterizes the theory. So I should therefore ascribe for a given value of this dimensionless parameter lambda, I should ascribe a cutoff. How do I ascribe the cutoff? By requiring that the physical mass of my particle is independent of the cutoff. So that's what we want to do. So the thing is, the sequence of theories which I need to construct in order to consider the low energy or the continuum limit means that lambda should have a hidden dependence on the cutoff such that it's very easy to solve this equation. So let's do it. So that gives you 2 times lambda exponential of minus 4 pi upon lambda, and then plus lambda square 4 pi by small lambda square d lambda exponential of minus 4 pi by lambda. So that tells you 2 lambda plus, did I get the signs right? I hope so. Cancel out the lambda. This is the equation which tells you how lambda should depend on the cutoff capital lambda such that the low energy theory has a mass which is independent of how you choose the cutoff and much lower than the cutoff of the theory. The reason why it's much lower than the cutoff of the theory is as follows. This equation then tells you that in the limit, so clearly that so let's try to solve this equation. So let me call log of lambda to be t. So this is d lambda by lambda square equal to minus t by dt by 4 pi. So this is what? Minus 1 upon lambda equal to minus t upon 4 pi plus a constant plus minus constant, doesn't matter. So 1 upon lambda of t1 minus 1 upon lambda at t2 is given by t1 minus t2 by 4 pi. So 1 upon 4 pi t is log. So 1 upon lambda of t1 as I mentioned, quantities like this which tell you how couplings depend on the cutoff are called beta functions. This is the beta function of lambda, and the solution of that equation tells you that given a value of the cutoff, so this is lambda 1 and lambda 2, If I specify for you the value of the coupling at one value of the cutoff, this tells you what is the value of the coupling at another value of the cutoff. Okay? It's also clear that this equation has a fixed point. So the fixed point has lambda equal to 0. That was the Gaussian fixed point to begin with. There is no other fixed point. There is no other solution to beta of lambda equal to 0. Fixed point is a solution. This is a solution of beta of lambda is equal to 0, and there is only a fixed point of lambda equal to 0. But if I now decrease lambda, then decrease the cutoff lambda, the coupling lambda actually increases. That just follows from this equation, and that's just given by the negative sign of this. So the small lambda which appeared as so if I plot the thing about lambda, this is the fixed point, this is the Gaussian fixed point, and the flows are like this. And in the large n expansion, at least the flows never end anywhere, it just goes all the way to infinity. The meaning of that we understood is that the theory just develops a mass. It is a gap with a finite correlation length, and that's what we found. Okay? We are expected to find, by writing down the nonlinear sigma model, that we will find that all these phi's sort of somehow get frozen like that. It's after all bundle of magnets. Didn't happen. It just got all scrambled over. If they were frozen, it wouldn't have this correlation which is like this. So this is the disordered phase of the system. Condensed matter physics called it disordered. High energy physicists called it massive phase. The same word. This is an example whose name is called asymptotic freedom. What this means, asymptotically means at very large energies. Very large energies means I can do the theory with a large cutoff. So there the coupling is very small, because this is going to lower and lower energies. That way is going to higher and higher energies. So the coupling goes to 0 at very high energies, and the coupling becomes very large at low energies. This is also the way the coupling constant of quantum chromodynamics, which is the theory of strong interactions, the theory which governs the interaction between quarks and gluons, behave. That theory is also asymptotically free. At small energies, it is like these quarks and gluons are very, very weakly coupled. They're almost free. And as you go to large energies, they become very strongly coupled, so strongly coupled that you cannot tear one from each other. This is like the baby version of that phenomenon. Okay, so let's go to the next step. Because perturbatively, this is g square n. This thing is small, right? And this as a function of g square n is not Taylor expandable in g square n. This is a non-analytic behavior in g square n. You could have never gotten this answer by doing any kind of perturbation theories g square for any fixed n. Same for QCD. You can never get the right answer from perturbation theory. Okay, so let's now do the next case, which is actually really interesting. I'll again write down the gap equation, explicitly do that integral, and now I'll find something new. P, there was this coupling g square n, and we found that the flows were all inside. It appeared to be an irrelevant coupling, and therefore we would have expected the low energy behavior to be given by a Gaussian theory. A Gaussian theory has no interactions, so this is what we called a trivial theory. You would have expected the theory is trivial, and we want to examine whether that is really true. Okay, this was just expectation by dimensional, classical dimensional analysis, but we want to really solve. Now we know solve the model, so we let's solve the model and find out what happens. So let's look at the gap equation again. So the gap equation was 1 upon lambda yeah. Oh, it's just a word. Because if there is a solution of this equation for sigma naught will appear as the mass of the field. A mass is a gap in the energy spectrum of the field. A mass is defined as the minimum value of the energy of anything, right? Because E square is P square plus M square. So P equal to 0 has M equal to 0. That's why it's called a gap equation. Historically, it's also a gap equation. This is sort of pretty much the way it happened in BCS theory of superconductivity, where equations were also this in older. It's very similar to what called Hartree-Fock approximation in many body theory. They're all the same kind of thing. They're all saddle point equations. So this becomes, so D equal to 3, this omega 2 is the volume of a 2-dimensional sphere, and that's 4 pi, and downstairs is 8 pi cube. There are many ways of doing this integral. This happens to be k. Evaluated at lambda and 0. So that's given by 1 upon 4 pi square. So when k is lambda, sigma naught is much smaller than lambda. This is like tan inverse of a very large number, that is pi upon 2. K is lambda, is much bigger than pi upon 2. So the first term is lambda, and the second term is no. So let's try. So the lambda sigma 0 tan inverse lambda upon sigma 0 at k equal to 0, this is 0 and that is 0. This is pi upon 2. So let's keep it that way. Pi upon 2 times sigma 0. So if you write for sigma 0, I made a mistake here. It cannot be 4 pi. 4 pi square. 4 pi square. I might have, 2. Yeah, good. So what is it? I only have the answer on my sheet, but might as well do it. Okay, Now, as I said, it's a bad thing generally to do, to deal with coupling constants which are dimensional. Okay. So, but here lambda has the coupling constant, too many lambdas here, anyway, has dimensions of mass. It's a dimension of is equal to 1, right. Yeah, so lambda has dimensions of 1. I messed up something, just 1 second. 1 upon g square d cube x, d phi whole square, right. So phi has dimensions of half, I mean generally and phi square was equal to 1. So if I put this thing here, so it is 1 upon g square. So this has dimensions of half and dimensions, the two of them has dimension 1 in, so dimension of phi is d minus 2 by 2 is equal to half for d equal to 3. So this dimension of 1 upon g square is 1. So dimension of g square, which is the same as dimension of lambda, is equal to minus 1. So I define lambda naught as given by lambda times lambda, and then I can write this thing as sigma 0 is this 2 lambda by pi clearly something interesting has happened now. It seems like sigma 0, or if I even was declared to be some real number, right. So square root of sigma 0, if I just consider this object, is also declared to be a real number, a positive thing. It's only in that case that you will get something which is which actually corresponds to a mass. So what you find, that something is happening when lambda naught is large enough, lambda naught is small enough such that this term is negative. So square root of sigma 0 is some negative, and clearly that something different from square root of sigma 0 is positive. To see this a little bit more, let us calculate the beta function of of lambda. I will not do the calculation, this is obtained by requiring to be independent of lambda. And the answer for that is okay. This solution is valid, it's 2 pi square. This is a very simple calculation. Take the derivative of both sides with respect to capital lambda and obtain this answer. So we said that, we'll say that it is valid for lambda 0 greater than 2 pi square. Okay. So if I draw the beta function as a function of lambda naught, there is 2 pi square here. So we know in this regime the beta function sort of looks like this, and when the beta function negative means it flows away from the fixed point. So I'll clearly show that there is a fixed point, and I have demonstrated so far that there is a fixed point at lambda 0 equal to 2 pi square from which the flows go out. I haven't told you anything about what happens for lambda naught less than 2 pi square, then I have to do something else. So at least we found another fixed point in the theory, apart from the fixed point which you are already expected at lambda equal to 0. It turns out, it will turn out in a minute, that this is indeed the exact form of the beta function, even for lambda naught less than 2 pi square, but it requires a little bit of more work, and actually it actually involves a little bit of more interesting physics. See, lot of this actually guided by physical intuition. What are you describing? You are trying to describe a 3-dimensional magnet, right? And for a 3-dimensional magnet, you know that at low temperatures the magnet is magnetized, right? At high temperatures the magnet gets disordered, it becomes a paramagnet. Okay. If you remember the way this lambda came into the action, it was 1 upon g square d phi square. So g square is roughly at the temperature of the theory. So you would expect for small values of g square the system should be magnetized. For large values of g square, I don't know what happens, you might have expected there is some phase transition somewhere. Okay. So let us now do the analysis for lambda naught less than 2 pi square. Now anticipating the fact that the system will get magnetized, let us now parameterize phi as follows. We will see you that why this. So there was an n-dimensional vector, I took the first component and called it r, sticked in a factor of square root of n for reasons which will become very clear in the moment. And then just do exactly what I did before. So the effective action in terms of phi's and pi's will turn out to be n upon 2 dr square plus half del pi square, which is these things, and then sigma pi square plus n r square minus 1 upon g square. This is just the original phi square, and this is your original del phi square just written out. Clear? Now we integrate out the pi's, just as we integrated out all the phi's, except now I am integrating out only the n minus 1 components. What will you get? You will get effective Lagrangian for sigma, which looks like I am not touching this part. Del r whole square n minus 2 trace log is just exactly like that. Plus n sigma r square minus 1 upon lambda. This r square just remains, that n just comes about, n g square n is lambda, so I have just written it that way. Okay. So for large n, now you can see why I stuck in a factor of square root of n here, because what it did was it sort of brought down a factor of capital N in front of the dr square. There was a factor of capital N minus 1 which came out of integrating out the pi's, and this factor of n was already there to begin with. Okay. So let us write down the saddle point equations for this. The saddle point equations for this would be, there are now two objects, sigma and r, because there is an overall factor of n outside. N minus 1 is the same as n. So I can replace this by n. overall factor of n. So, I should take the whole thing and write the saddle point equations for that. So, there will be one saddle point equation by, I will assume the saddle point as r equal to r0, a constant, sigma equal to sigma 0, also a constant in space. So, del sigma gives rise to the equation r naught square so I'll just do 3 dimensions now. And del r gives you the equation sigma 0 r0 equal to 1 equal to 0, because del r it just is only thing which is thing here, because r has been assumed to be a constant, there is nothing from there. This equation has 2 solutions. One solution has sigma 0 not equal to 0 okay, and so then r0 is equal to 0, and the other solution is sigma 0 equal to 0, and r0 can in general be non-zero. The solution which has sigma 0 not equal to 0, we already saw that, right, and that solution was not valid for lambda which is less than 2 pi square. Okay. So, it must be that for lambda less than 2 pi square, it is picking up this solution. So, let us see what happens there. For that solution, it becomes actually quite trivial. It tells you that r naught square, so I just take this equation plus half, I don't know why there is a half, I think there is no half, forget about factors of half. That integral is trivial to do, and what happens is you get an equation which is plus this is equal to 1 upon lambda. So, what you get is r naught square is lambda by 2 pi square, where again lambda times this is this lambda naught. And here you can see that this is clearly the solution which is valid when lambda naught is less than 2 pi square. Okay. So, what is happening? For lambda naught bigger than 2 pi square, I did not find any hint of the system will magnetize it. In fact, I found that all the components of phi were on an equal footing, they were all madly oscillating, and they were so madly oscillating that the system got disordered and generated a gap in the spectrum. The correlations were just, that is what we call a paramagnet. Okay. For lambda naught less than 2 pi square, what we found is that sigma naught was 0, but r naught was non-zero. R naught was one component of phi. The expectation values in my previous calculation, the expectation values of the phi I are 0. Right? That is why the system was not magnetized. The expectation value of phi is non-zero, but the way I have chosen to parameterize it, it is only one component, it is just choice of component, it is choice of frame, the choice of the coordinates in field space. So, the expectation value of phi is not 0, and it is in fact given by this equation. Okay. So, this tells you the order parameter of the theory, which is the magnetization of the theory, how it depends on the coupling lambda. Okay. Like everything else, the expectation value of r naught should not depend on the cutoff. So, you should define a beta function from this, and you get exactly the same beta function. So, I leave it as an exercise that you require r naught to be independent of lambda, gives you a beta function for lambda naught, which is exactly lambda naught by lambda naught square by 2 pi square, which is exactly the same as before. What happened to the pi's? The pi's had expectation value which were non-zero, And as I mentioned, there is no mass term for the pi's anymore because sigma naught was 0, right. So the thing which would have gave a mass to the pi's was not there. So in this phase the fields pi's are massless. This is a dynamical demonstration of something called the Nambu-Goldstone mechanism. You started with a theory which has a symmetry ON. That was what it started out with. We found a phase of the theory. So let me complete the flow diagram from this. This beta function tells you that there is a non-trivial fixed point here for d equal to 3, which, sorry, other way around, sorry. Magnetized phase and a disordered phase. In the magnetized phase, we say that ON is spontaneously broken. Why? Because if ON was a symmetry, it couldn't possibly be true that phi would acquire an expectation value as an average value. But here it did. R had a saddle point. However, there is still a symmetry of rotation of all these pi's among themselves. So there is still a symmetry in the theory. The symmetry spontaneously broken down to ON minus 1. This is an example of spontaneous symmetry breaking, and in spontaneous symmetry breaking there is a famous result that the number of broken generators in simplest situations, the number of broken generators is equal to a number of massless particles in the theory. So let us calculate the number of broken generators. ON has n times n minus 2 generators. ON minus 1 has n minus 1 times n minus 2 generators. So the number of broken symmetries are given by n minus 1 by 2 n minus n minus 2. That's n minus 1, which is precisely the number of fields pi 1 to pi n minus 1. There are other parameterizations of these fields which make it a little more symmetric instead of writing it in this particular form. The really nice way of doing it is to take out a magnitude and write it in the Lie algebra of the ON. But I think this is good enough and shows the physics very, very clearly that what we have found is that there is an ultraviolet fixed point in the theory. It's ultraviolet because as you go towards this, you are going to higher and higher energies. This is the direction of low energy physics. Okay? So if I ask for this model, if I looked at the point, the non-trivial fixed point here, I see all the flows coming here, and I ask the question, are they coming from some non-trivial fixed point of the theory? The answer is yes. In the non-trivial fixed point of the theory, there is another scale invariant theory there, and as it flows down, I get to a point where by and large all the fields are free and there are n minus 1 massless particles. It's not very hard to see that the fluctuations of the field are going to be massive, so that just remains out there. Okay. And what we have found, that if I am a little bit to the right of this, if I start a little bit to the right of this, it doesn't go to this magnetized phase, it sort of flows all the way out, the theory disorders itself and generates a mass gap. So here are the two pictures. Oh, time is up. So this is for d equal to 2. There is always a fixed point here. The flows are like that. For d equal to 3, the flows terminate at an ultraviolet fixed point. For d equal to 4, it's d equal to 3, d equal to 4. A theory which only has irrelevant operators, as I repeatedly say, at low energies it just behaves like a trivial theory. In the particle physics, historically they were called non-renormalizable theories, and non-renormalizable theories are supposed to be very bad. The reason why they were very bad was that if I didn't understand that they correspond to free theories and tried to say that these are interacting theories, then it sort of doesn't make sense in the following sense, that because they are irrelevant couplings, they will depend very sensitively on the values of the couplings at in the ultraviolet, namely at the microscopic level. If a theory has relevant parameters, what this means is that the dynamics in the relevant parameter doesn't depend very sensitively on the physics of the microscopic theory. Okay? So this is the reason in modern language why non-renormalizable theories were supposed to be bad. They were bad except when the couplings were 0. But then nobody is interested in a theory whose coupling is 0, so people didn't used to bother about non-renormalizable theory, it was such a big deal to show that QED is renormalizable, it showed that the theory of weak interactions is renormalizable and the theory of strong interactions is renormalizable, because it gave you the ability to predict low energy behavior of the theory without the detailed microscopic knowledge of thousands of parameters of the microscopic theory, and that's what we want. Okay? It appeared that these theories were not of this form. And it has always been a question whether if I get a theory, this concept of normalizable, renormalizable or non-renormalizable were always tied with perturbation theory. Perturbation theory is weak coupling, which is sort of looking around this fixed point. So if you're looking around this fixed point, oh, I drew the wrong diagram, sorry. So if I look around the fixed point, I do a perturbation theory and find the theory as an irrelevant operators, I mean all the operators are irrelevant, there is no relevant operator in the theory, then I say it's non-renormalizable. But then you got to really ask whether there is a non-trivial fixed point somewhere out there. If there is a non-trivial fixed point somewhere out there, there is nothing wrong with this theory. In fact, this phase of the theory pretty much looks like that phase of the theory, which is a perfectly well defined thing. For d equal to 4, this doesn't seem to happen. So these are genuinely theories which have to be thought of as some models, some low energy effective actions, and the cutoff does play an important role in those theories. For d equal to 4, not in this model. D equal to 4 Heisenberg model is a disorder phase? Probably doesn't, right? Are there magnets in 4 dimensions? Or paramagnets in 4 dimensions, huh? This large n. I don't know what the finite n answer is. I would think not. Huh? Oh, it has a paramagnetic phase, or it's always magnetized?
Equal to 4.
Because typically fluctuations decrease as you go to the mean field classical results are reliable beyond v equal to 4, right? So I would expect that system is always magnetized. Huh? That's linear sigma model. That's a different thing. Except the problem is that there you haven't fixed S square equal to 1. But you put a potential for, if we write down a model that has a different behavior, this is fine. It's called the linear sigma model, where you have allowed actually the magnitude of phi to fluctuate. That is a very different. I thought I'll do the linear sigma model very briefly tomorrow, and in the very beginning, just to introduce some concepts of large N in there. But that has a very different behavior. The linear sigma model in 3 dimensions, the picture for the linear sigma model is a little bit different. This coupling here, lambda, is dimensionless in 4 dimensions, and it has dimensions of mass in 3 dimensions. So it's actually a relevant. It's actually a relevant coupling in 3 dimensions. So in d equal to 3, so let me not call it lambda, let me call it something else, mu. Event at the fixed point, it actually flows to an infrared fixed point. Because this is like Wilson Fisher, right? I mean, so this.
But linear sigma model is just an ordinary Wayne model.
Huh?
The ordinary Wayne model.
Yeah. So it's an, huh? It's a Ising model. Yeah, but that's a little bit different because of the constraint of phi square equal to 1. It makes a big difference actually. Yeah, it's a continuum limit of Ising, right? The same universality class at phi going to minus phi. It is two. See, the point is that when you talk of universality classes, you basically talk about behaviors near fixed points, right? So behavior, you don't really care how you got to that fixed point. So the behavior around this fixed point is actually the same as the behavior near this fixed point, but you have arrived it in a different way. That's what it is.